So in this video we're going to talk about some vector math. If you remember in the last couple of videos we talked about differences between scalars and vectors. So let's recall that scalars are just a measure of magnitude and vectors are the measure of both magnitude and direction. When you want to add or subtract scalars, you simply just add the numbers. For example, weight is a scalar or mass is a scalar. I could say, 4 kilograms plus 5 kilograms is 9 kilograms. But if I want to add vectors, which consider both magnitude and direction, it's a little bit more complicated. So let's first talk about visually what does a vector look like. There are two parts to a vector, both magnitude and direction. So if I draw, say, this vector, the length of the line, so like all of this, corresponds to the magnitude of the vector, while the arrow, the direction of the arrow, corresponds to the direction of the vector. So there'll be like some angle here, we'll call it theta, that tells me what direction the vector is going in. Okay, so let's look at adding two simple vectors. Alright, let's say I have an airplane traveling north at 110 kilometers per hour, and then I also have a tailwind, which is, let's say that's 11 kilometers per hour, also in the north direction. So the resulting vector, the speed of the plane, is actually just these two vectors added together, which is easy because they're in the same direction. So that's really just 121 kilometers per hour in the northerly direction. Okay. Now let's say I have the same airplane. That's not a very straight line. So same airplane traveling north at 110 kilometers per hour. Let's say now I've got a headwind. So that would be a southerly wind that is 11 kilometers per hour. Okay, so my resulting vector in this case is this guy. I need to subtract the vectors because they're in opposite directions. Okay, and that's going to be, let's see, so 99 kilometers per hour in the northerly direction. Okay, let's look at a slightly more complicated example. Okay, now let's say I have another plane. Again, traveling north, and let's say it's traveling at 80 kilometers per hour. And let's say that I have a westerly wind traveling at 60 kilometers per hour. What is the speed and the direction of the plane? Okay, so, the plane is directing itself at 80 kilometers per hour north, but the wind is going to push it slightly off that track. So it's actually going to look something like this. That's the resulting vector, the actual speed and direction of the plane. And to find the length of that, notice that this is a right triangle. So I can use Pythagorean theorem, and I get that the plane is traveling at 100 kilometers per hour in the northwesterly direction. And if I wanted to find this angle, I could just use a bit of trig, but we won't do that right now. Okay. So we see that if we want to add vectors together, that are at right angles, so like here was my right angle, I need to consider Pythagorean theorem. If all the vectors are collinear, so like on the same line, like these guys, then I can just add or subtract the vectors depending on if their directions agree. When the directions agree, then I just add the vectors, right? And when their directions are in opposite directions, I subtract the vectors. Okay, so let's look at kind of working backwards from this scenario right here. So most of the time, I'll actually be given this vector, the resulting vector, and I'm going to want to work backwards to figure out what was the direction in terms of the x-axis and what was the directions in terms of the y-axis. Or what was the horizontal vector, component vector, and what was the vertical component vector. Okay, so let's say I have a cannon shot at some angle from the horizontal. We'll call that angle theta, with a initial velocity. We'll just call that v. Okay. And let's say that I now want to break this up into the horizontal component, which is the vector that would describe the motion of the cannon horizontally, and the vertical component, so a vector that describes the motion of the cannon vertically. So what I can do is set up a right triangle and kind of work backwards from the last problem. So you've got to know a little bit of trig to be able to do this. Let's say that I'm going to call the vertical component y and the horizontal component x. I'll just give like a brief review. You should know sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. And then you probably heard the acronym SOHCAHTOA. Okay. So if I want to describe, let's say, the vertical component, I would do sine of theta, which is the angle that the cannon is shot at, equals opposite, so opposite the angle is y, over hypotenuse, which is v. And the hypotenuse is always the side opposite the right angle, so that's always going to be the hypotenuse. Okay. Solving for y, which is the vertical component, I get that y equals v sine theta. I can do kind of the same process to solve for the horizontal component, x. Okay, so cosine of theta is adjacent, which means side next to, so the side next to the angle is x, over hypotenuse, which is still v. Therefore, the horizontal component in terms of x, or solving for x, is v cosine theta. So basically what this is saying is that the vector that describes the horizontal motion here can be rewritten in terms of v cosine theta, and the vector that describes the vertical component here can be rewritten in terms of v sine theta. Okay, so this is really important when we talk about projectiles in the next video. We're going to use this relationship to break vectors up into their two components to actually be able to solve real-world problems involving projectiles.